Today we will be starting with the new topic of two-way slabs, and in the previous lecture we completed one-way slab numerical. So two-way slab is also identical in steps, just a little bit modifications here and there. And as you know, the two-way slab is Ly by Lx less than or equal to 2. So first we will be finding the Ly by Lx ratio, and then if it is less than or equal to 2, we will understand that it is a two-way slab. And then we have to select the span to depth ratio, right? And again the given thing would be long span will be given, short span will be given, and loading will be given. Not necessary Ly and Lx is given. What I am exactly saying is this long span and short span can be given in terms of clear spans and not effective spans, whereas Ly and Lx are effective spans. Step 2 is trial effective depth using the span to depth ratio. Now for two-way slab, we have this clause 24.1 of IS 456-2000, and here it is written that for slabs spanning in two directions, the shorter of the two spans should be used for calculating the span to effective depth ratio. That I already explained that why shorter one is important. For two-way slabs of shorter span up to 3.5 meters with mild steel reinforcement, so what we have here is 3.5 is Lx and steel should be mild steel reinforcement. Then and also the loading class is up to 3 kilonewton per meter square. So this is actually live load. Vertical deflection limits for loading class up to 3 kilonewton per meter square. So these conditions which are there, simply supported slabs 35 and continuous slab 40, these are your span to depth ratio, and these can be adopted only when your Lx is less than 3.5, less than or equal to 3.5. Second, your steel is a mild steel, and third, your live load is less than 3 kilonewton per meter square. Okay, so if these conditions satisfy, then you can use these span to depth ratio. Otherwise you will have to use the span to depth ratio that we saw previously, that is for beams. So when Lx is less than 3.5, live load less than or equal to 3 kilonewton. Now for mild steel they are saying it is 35 and 40, but if we use HYSD, that is grade Fe 4.5 or above, then we have to multiply these values by 0.8. So 35 into 0.8 and 40 into 0.8, whatever that comes. I think this comes out to be 28 and this comes out to be 32, I believe. So you understood, right? For the simply supported slabs, if it is HYSD, we will be using span to depth ratio of 28 given that these conditions satisfy, and for continuous slabs we will be using 32 if it is HYSD and these two conditions satisfy. So span to effective depth is equal to whatever ratio that you have multiplied by the modification factor, and yeah, this is short span, so effective depth will be short span upon S by D ratio into modification factor. So D is short span upon span to depth ratio into 1.2. I am assuming the modification factor because in the start we have to assume one modification factor, and therefore this depth is called as a trial effective depth because we are not sure about this modification factor value, and later on when we progress in the numerical we will be verifying whether this modification factor that we used in step 2 is okay or not. Fine, so here we get our effective depth. From effective depth we can find the total depth. So D plus clear cover plus diameter. So this diameter we can use 10 or 12 mm most probably. If required more than that, then we can use those diameters as well. Now this was for Lx when it is less than 3.5 and live load when it is less than 3. What will happen if Lx is greater than 3.5 and similarly live load greater than 3? Then we will be using these span to depth ratios. Now these span to depth ratios we have already seen, and these are used for the beams. And if it is a cantilever slab, the span to depth ratio is 7, which is not mentioned here, but we have seen that clause before. After step 2, we will move to step 3, that is load calculations. Now load calculations will again have the same things: dead load, which is D into 25, floor finish, if it is not given you have to take it from IS 875 part 1, live load if it is not given you have to take it from IS 875 part 2, total load will be the summation of these, and ultimate load will be 1.5 times the working load. So this will be ultimate load. After finding ultimate load, we need to find the moments. Now talking about the moments that come on the slab, the entire two-way slab process is given in annexure D of IS 456, and of that annexure D, D 1.1 says that the moment will be in two directions. We'll be designing our slab in two directions. That's why it is called as two-way slab. And these are the formulas that are prescribed by IS 456, and what it says is MUX, that is moment along short span, is alpha x into WU into Lx square, and MUY, moment along long span, is alpha y into WU into again Lx square, not Ly square. So in both the cases, the design length that we'll be using is short span itself, no long span to be used anywhere. Now alpha x and alpha y, these are two coefficients that are given in IS 456 table 26. We'll see that in just a moment, but before that there is a concept that you should learn. Now again it is given in annexure D, D 1.2. What it is saying is slabs are considered as divided in each direction into middle strips and edge strips, the middle strip being 3/4 of the width and each edge strip 1/8 of the width. So what it is saying is that the slab is considered to be divided in three parts. First is the middle strip, and it is 3/4, that is 3/4 of this entire length is Lx, right? The short span is Lx, so 3/4 of Lx, and the remaining part would be 1/4 of Lx, and since it is divided into again 2, so this will be 1/8 Lx, this will be 1/8 Lx. So these are your edge strips, these are your middle strips. Same way, the long span can also be divided. So the long span is divided into middle strip of 3/4 Ly and these two edge strips which are 1/8 Ly. So this is how our slab is divided. If I want to show it on a single slab, it will be looking something like this. So this is your edge of the long span one, and this area is the middle part for both cases, right? Table 26 that gives us alpha x and alpha y value. Now the first part of table 26 which deals with these 9 cases, it gives you alpha x and alpha y. This is alpha x, alpha y, and both of them, alpha x and alpha y, they depend on Ly by Lx ratio. So these 1, 1.1, 1.2, they are Ly by Lx ratio till it is 2. So this is for a two-way slab, right? And here for alpha y, it does not depend on like for any Ly by Lx ratio, it is a single value. But for alpha x, you will have to interpolate between them. Now I will explain you all these 9 cases. These 9 cases are except the simply supported case, everything is given here. So what this interior panel says that if there is a slab like this, okay, then along all the edges there will be a slab continuing. So there will be a slab continuous along short edge, there will be a slab continuing this. I will show it like this. So there is a slab continuing along the long edge on both sides, there is a slab continuing on the short edge on both sides, and this is in between panel. So this panel is what we are designing, and that is called as an interior panel. The second case, that is one short edge continuous is given. This is a mistake in the IS 456, that it is a printing mistake, and it says that it is one short edge discontinuous and not continuous. So one short edge discontinuous meaning that there is a slab along the long span, along both long spans, and there is a slab along one short span. So one short span is discontinuous, that is, it is not continuing any slab on one side. So if this is the condition, then it is condition number 2. Let us talk about the third one. One long edge discontinuous. It means that there is a slab on three sides and only one long edge there is not continuing. So if this is the case, it is the third case. Then fourth case says two adjacent edges discontinuous. So if the slab is continuous like this, one short edge and one long edge, but these two adjacent edges are discontinuous, then it can be considered into case number 4. Then two short edges discontinuous. So if the slab is like this, where two short edges are not continuing, then it comes under 5th. Then two long edges discontinuous. So if the slab is something like this, that is two long edges, they are not they do not have any slab on either side, then it is under case 6. Case 7, three edges discontinuous. So if this is the case, that is either one short edge is continuous and the three edges are discontinuous, or one long edge is continuous and the other three are discontinuous, then it should be in case 7. Sorry, case 7, right? Okay, case 7 and case 8 both I have shown you actually. Case 7 says that one long edge is continuous, that is this one long edge is continuous and other three sides are discontinuous. Case 8 says that one short edge is continuous, so only the slab is continuous only along the one short edge and other three are discontinuous. And case 9, it says that all four edges are discontinuous, but these four edges are not simply supported, they are fixed. So all these 9 cases I have told you. After that, this is table 27, which speaks for slab spanning in two directions for a simply supported slab. So all these previous cases were either having a continuous slab somewhere, or if all the four edges were discontinuous, it was not a simply supported slab, but it was a continuous slab. Sorry, it was a fixed slab. For a simply supported slab, we have this table number 27, in which alpha x and alpha y both depend on Ly by Lx ratio. In the previous table, only alpha x dependent on Ly by Lx ratio and alpha y was same for any Ly by Lx ratio. So if it is given as a simply supported slab, you will have to interpolate between them and get alpha x and alpha y ratio. This would be given to you in exams. Definitely it should be given. After getting alpha x and alpha y, you can directly find your mu x and mu y. That is a moment along short span and moment along long span. After getting that, we need to check the maximum moment that the slab can carry. So for the effective depth that we had provided to our slab, depending on which steel is used, we can find the mu max, and based on that we will understand that what is the maximum moment carrying capacity of our slab, and if it is greater than these two moments that we had just calculated, then the provided depth for our slab is sufficient. But if your mu max comes less than mu x or mu y, then you will have to revise the depth again and you will have to do all the calculations again. Okay, this was for step 5. Step 6, main steel. Again, the steel will be given in two directions. First is along the short span, so this is along short span and this is along long span. Okay, so ASTX is 0.5 CKB dx. Now dx is the effective depth for your short steel, and let us say that this is your dx. Okay, this depth is dx, and dx will be what? Total depth d minus the clear cover minus the dia by 2. So dia of this steel diameter by 2. Okay, so phi x I have written, that is the diameter along the short span or along the x span, and dy will be the depth of your secondary steel, that is the steel that you are providing along y direction, and if this is that steel, then it will be capital D minus clear cover minus the dia of your steel in x direction minus half of dia of steel in y direction. So this is how you will have to calculate both dx and dy, and you will have to put them in these two equations. So when finding ASTX, that is steel along short span, you will have to use dx in both these places, and here also you will have to use MUX and MUX, MUY, and in ASTY you will have to use dy in both these places, and then find steel along short span and along long span. After finding steel in short span and long span, we will be finding the distribution steel, AST distribution depending upon the grade of steel. It is 0.15% of BD or 0.12% of BD, where B, you know, B is 1000 mm because we consider a strip of 1 meter, right? After finding these, now there is a concept in two-way slabs. See, what happens is, consider this to be a two-way slab and I am not giving restraints on these points, okay? These points I have not given restraints, that is I am not holding them back. You can see these are the supports that are holding this edge, this much edge. Here this much edge is being held, here this much edge is being held. So the corners of the slabs are not being held. Let us see what will happen if when we load such a kind of slab, and let us see the deflection pattern. So this is how the slab is going to deflect, and can you see these edges, the corners? All the corners have gone up. All the corners have moved up. So what this behavior says that when the restraint is not provided, the behavior of a two-way slab is to lift its corners up. It wants to lift its corner up, but when we provide the supports here or when we provide the restraints on all the corners will not be lifted up, but still inherently the slab wants its corners to be lifted up, right? To give you a very simple analogy of this, consider a car that is moving like this, okay? Consider a car moving in this direction. Now it is freely moving in this direction. What I will do now is I will put a wall here, okay? Now can it move? Can it keep on moving in this direction? No, it cannot keep on moving, but still its wheels are turning, okay? Its wheels are turning, so it still wants to move in this direction, but because of these walls it is not able to move in this direction. Similarly, when this wall was not there, this car could move easily. Similarly, when the supports are not there, the corners can lift up easily, but when we provide this wall or when we provide the supports, it cannot move up, but still it wants to move up. Now how should I stop this car from moving? I should apply brakes. When I apply brakes, this car will stop moving. The thing similar to brakes that we have in slabs, which will restrain the corners from lifting up or which will prevent the corners from lifting up, is called as torsional steel. And how torsional steel is given? This is how it is given. The torsion reinforcement shall be provided at any corner where the slab is simply supported on both edges meeting at that corner. It shall consist of top and bottom reinforcement, each with layers of bars placed parallel to the sides of the slab and extending from the edges a minimum distance of 1/5 of the shorter span. So the span of this torsional reinforcement is 1/5 of the shorter span. So it is kind of a square edge, square mesh shape type of reinforcement that we give at the corners, so that our corners are prevented from lifting up. It is same like the brakes that we applied to the car, so that it stops from moving in the same direction. The area of reinforcement in each of these 4 layers shall be 3/4 of the area required for the maximum midspan moment in the slab. So the AST that we provide in this is AST torsion is 3/4 of ASTX. ASTX would be the maximum moment definitely, because the shorter span will attract more moment. That's why I've written here ASTX directly, but what they have told is area required for the maximum mid-span moment in the slab. Okay, so it can be ASTY in certain cases, not in all cases, in certain cases, but in most of the cases it will be ASTX. Fine, but what they have told is it shall consist of top and bottom reinforcement. How this is exactly given in a slab is, I have drawn here a 3D diagram in AutoCAD, and this is how that torsional steel will look at the corners. So you can see that there is a this bar is bent like this. So we have these C type of bars, we have bent it like this, and then inside we have another C type of bar which is placed this way in perpendicular direction. So this is going to form a mesh, right? This is the top mesh and this is the bottom mesh. Fine. So this is how we give the torsional reinforcement in the steel. Step 7 is spacing. So maximum distance between bars in tension, this we have already studied. Main steel, it is minimum of B into area of 1 bar upon ASTX. Second criteria is 3D. Third criteria is 300 mm. Spacing Y, minimum of these three criteria again. Now we will have to consider two spacings because we are providing steel in both X direction as well as in Y direction. So both the times we will have to give spacing. Spacing of torsion is 1000 into area of 1 bar upon AST torsion. And for distribution steel it is minimum of area of 1 bar upon distribution steel. Second criteria is 5D and third criteria is 450. So all of this I had explained in my previous videos, and how we get it from this clause 26.3.3. Next step is check for shear. Now shear force coming on slab will be VU into WLX by 2. Shear capacity of concrete, this is the shear force that is coming on the slab. We will check what is the shear carrying capacity of our slab, VUC. So VUC is K into tau C into BD, where K is dependent on the overall depth of our slab. So wherever our overall depth lies here, we will have to interpolate it and find K. Tau C will depend on again two criteria. First is percentage of tension reinforcement and second is FCK. And then from table 19 we will have to select the percentage of tension reinforcement, and based on the grade of concrete we will get our tau C, that is the shear the strength of concrete. And from VUC and VU we can say that if VU is less than VUC, then the slab is safe in carrying the shear, but if VUC is less than VU, then you will have to either alter the depth of the slab or the steel provided of the slab. Altering the steel is more convenient, right? Next step is limit state of serviceability, and that is the check for deflection. So we have these basic span to depth ratios, and now these are for the case when Lx is greater than 3.5 and your live load is greater than 3. For Lx less than 3.5 we had seen that it was, I think for Lx less than 3.5 it was for simply supported it was 35, and for continuous slab it was 40. So these span to depth ratios we have multiplied by the modification factor. You will have to find the modification factor based on the area of cross section of steel required and area of cross section of steel provided. Based on that, when we find the modification factor, if the modification factor found here is greater than what we had taken in step 2, then our design is safe. Otherwise you will have to revise the steel or you will have to revise the depth entirely. Next is check for the development length. So development length concept also I had explained in my previous video. LD is phi into sigma s upon 4 tau BD, and in my previous video lecture I had shown how this formula is coming. Tau BD is the bond stress of your concrete. For deformed bars, this tau BD has to be increased by 60%, and if the bar is under compression, it has to be again increased by 25%. Now, this should be less than 1.3 times M1 upon V plus L0, where M1 is mu by 2, mu is the maximum moment in x direction, V is the shear force in x direction, and L0 is dependent on various types of hooks that we give. That also I had shown in my previous video lecture, so you can check that. Now let us check the detailing part of the slab. So what is given in this clause D 1.4 is tension reinforcement provided at mid-span in the middle strip shall extend in the lower part of the slab to within 0.25 L of a continuous edge or 0.15 L of a discontinuous edge. So here in this slab what we are seeing is this is a discontinuous edge, and this is a continuous edge, and what it is saying is that the tension reinforcement, this tension reinforcement, okay, it has to extend to a depth to a length of 0.15 L in the discontinuous edge, and it has to extend to a length of 0.25 L in continuous edge. Over the continuous edge of a middle strip, the tension reinforcement shall extend in the upper part of the slab of distance of 0.15 L from the support, and at least 50% shall be extended at a distance of 0.3 L. So here it is 0.1 L near the discontinuous edge, but at the continuous edge it should be extended to 0.15 L. This is the tension reinforcement, the same tension reinforcement that is going up. So we have extended on the continuous edge at a distance of 0.15 L, and this clause particularly speaks about only the continuous edge, not the discontinuous one. So here we are providing 0.1 L. Okay, here we have provided 0.15 L, and what it is saying is that at least 50% shall extend at a distance of 0.3 L. So this tension reinforcement, 50% of this tension reinforcement shall extend in the next continuing slab for a distance of 0.3. Now L dash I have used, L dash is nothing but the span of this next slab. So the span of this slab, first slab, is L, the span of next slab is L dash. So 0.3 times of this L dash has to be extended here. So from this point to this point is 0.3 times L dash, and this is the same bar that is of this tension reinforcement. So this is that clause. Now what it is exactly what we are doing is that, first of all, this is the tension reinforcement that we are bending up. Now these bending is half of these tension reinforcements we are taking up. Half of the tension reinforcement we are bending up, first of all. Then what it is saying is that again 50% of this we have to take in the next slab. So again half of those we will be taking in the next slab. Okay. Same is done from the adjacent slab as well. This is 0.15 L dash, and again this is 0.25 L dash, and half of this will be again taken to 0.3 times L, that is in this slab. So I hope you got what we are exactly doing. We are taking this tension reinforcement, and then half of it we are extending in the adjacent slab by 0.3 times L dash. L dash is the span of the adjacent slab, and again the steel from adjacent slab is also coming into this slab, and that is also for 0.3 times L. So this is how the detailing has to be done, and it is not complete, like we have to give the distribution steel and a lot of things are there. So this was it for today's lecture. In the next lecture we will be solving a numerical. Till then, take care. Thank you.